future. You can follow up with questions or anything. The goal here, though, was to keep it relatively simple and provide an on-ramp to autonomous racing, autonomous mobility, robotics, the whole 9 yards. So
David, it's not shared. Can you share?
oh, it's not sharing. Why isn't it sharing? Let's see here. Did I share? There we go.
I can see the car.
Oh, you can see it?
Yeah, I can see the car. I think you might have to.
No, it's not the car. It was the PowerPoint that I wanted to.
Oh.
Are we
yeah,
not
that is
seeing the
not it.
PowerPoint? Hang on a minute. Hang on. Oh, here we go. Bam. And how are we now?
It's firing up. There we go.
Now,
Yeah. Okay. Okay. Let me get rid of this. Okay. So. Okay, let's. All right. And why aren't we not flipping screens all of a sudden when we hit return or the down arrow? Gremlins. All right. Let's see here. Well, this is interesting. Okay, so we're just going to do it old school. All right. You can see this. Let's see if this works now. Okay, fundamentally 4 functions in autonomous vehicles, autonomous bots. Some might say there's 3, but at the end of the day, perception, localization, planning, and control. So perception, what's going on in the environment. Localization is the mapping and things like that. Where am I? Planning is whether you're going to follow a route, a series of waypoints, or otherwise to get to go where you're going. And control is really more the hardware stack, whether you're using ESCs for smaller cars like we use, or ODBC or CAN buses in the larger cars. The fundamentals are always the same. The neural networks are very, very similar. They just get a little bit more sophisticated. But as far as the hardware goes, LiDAR, camera, GPS, radar, localization on the map, point clouds, the GPS, camera, and LiDAR as well for point cloud data, doing localization with point clouds. Sensors, again, this is in your compute stack and algorithms for how you're going to determine where you're going, and then control being the hardware side of the equation, vehicle, physical vehicle interface. So on your average autonomous vehicle, you'll have like a LiDAR up here on top. You'll have a forward or an internal facing camera down here, and then more radar, LiDAR, or cam sensors, usually around the front, and then possibly also on the back. And in the big world out there, there's already some full-size autonomous racing that's getting started. RoboRace is a manufacturer series. India Autonomous Challenge was something unique to college students. It's going to go off this year at the Indianapolis Motor Speedway. This in September, I believe, October, I believe it is. So this is going to be interesting. That's never been done before. But the problem with Indy is it's a high barrier to entry. It's $1 million car that the students are working with, and it just doesn't enable any kind of community education. So we have there with the world of the smaller vehicles. And this, sorry about that, this is from the F-110 group. There's a bunch of different groups out there, but this is a little bit more sophisticated model. But we're going to get rid of the LiDAR because we're going to follow JetRacer approach, and that's from NVIDIA as an entry point. The car that you saw, Reiner, is a member of our parking lot nerds team in the clip that Alex showed earlier. The car he was racing against for first and second place was actually a JetRacer construct. This is called F-110 here. It's a little more complicated, but you can see down here again, perception, planning, and control. They use ROS. Wish we had more time. This is a very relevant subject. Look up the AutoWare Foundation. ROS is big in autonomy, leverageable on the car and on the bots. But for, again, the goal here was a real fast, simple on-ramp. So the perception, planning, and control, as well as all of these algorithms, are going to be handled by JetRacer and combined down to a fairly simple algorithm. So on the hardware side, to make this happen, and I got to watch my time here. So for a simple RC car is enough to get you started. Got a motor, got an electronic speed controller, got a receiver, space for a battery and a servo controller. You can pick those up for next to nothing. There's nothing special to it. You throw a platform on top of that, and then you get yourself either a Jetson Nano or a Raspberry Pi. You can do it with microcontrollers, but the Nano from NVIDIA, which is under $100, gives you a lot of AI capability. It's a little more powerful than the Raspberry Pi, but you can certainly do it with either. This is the car that I have sitting. It's a slightly larger car, but you can see again here, it's the same thing. Here's an NVIDIA Nano. Here's a Raspberry Pi 2 cam. Down here is a servo controller, which you need to go from the Jetson to the ESC. And then here we have a multiplexer that's allowing you to switch between remote control or manual control. And so this, just to kind of give you an idea, is the range of what you can do. This is a 1/28 car that works on vision only. It's a little bit different. This is a Raspberry Pi based on a donkey car, which we'll look at in a sec. And Alex spoke about earlier. This is the primary workhorse for DIY robocars. This is a regular RC car converted with NVIDIA Nano to run JetRacer code. And this is now, we're kind of in our group starting to explore a little bit the world of off-road. That changes everything, as does going outdoors. So here, this is a 1/8 scale Traxxas Slash. This is a 1/10 scale TC4. I believe this is also 1/10 or 1/12 scale, and this is 1/28 scale. So you can do things in all sorts of different sizes. I just wanted to mention here that a lot of people run their cars open like I have it here in the picture. That's good. The more people get faster, the more interesting it gets, the more you're going to crash. So it's good to kind of think of some sort of roll bar or protection for your unit. On the software side of the equation, and I've got a couple of seconds here. So we're going to be following or very briefly, the NVIDIA JetRacer GitHub repo. That's where all of this stuff is based. Those are Jupyter notebooks, very easy to follow. Let me see if I can actually come out of this for a moment and go over here and see if we can actually get this guy going live, because he's hooked up. Where am I here? Let's go to this one. Come on. Where's my Jupyter lab?
Dave, I think it's right there. You just have to maybe maximize the window, the browser window.
What's that, Alex?
Maybe you have to maximize the browser window.
Okay. So
Yeah. Okay.
here. Let me just pull this over. Okay, so now we're in one of the first Jupyter notebooks called Basic Motion. And just to give you an example here, after you've imported these basic requirements, the next step, you can start to decide on your steering. And I'm on the laptop, but you'll see the car here. If I change the steering value as you start to calibrate things, oops, wait a minute. There we go. Let's try that again. I had it set to the other side. See if we can get those wheels to turn. And why aren't our wheels turning? There we go. And then, okay, and then let's set it back then. So you should sort of be able to see, there you go. The wheels jump in relation to this. If I go down lower, I can start to do the same thing with the throttle. I'm going to skip this right now because this is a pretty powerful car. It would start, you'd make a lot of noise, and we're a little bit tight on time, so I'm not going to worry about the throttle. But again, you could put these same values or different values in here, and this thing would start to rock and turn and so on and so forth. And once you've gone through that side of the equation, the next folder that you go to is called interactive regression. That's also the basis of how the neural network works. And so you would pick up the information, you register the camera. I'm not sure it's been sitting a while, whether it's going to like this or not. We'll see it. Oh, it did. It may take a few moments. And this is basically exactly what you would be doing in the process. And then if we get lucky here, there we go. That's the library behind me. I'm sitting in an empty room. And with this, you would actually now start to train the vehicle by essentially putting a dot on the screen of where you would want it to go. So normally we'd have a track or something in front of it here, but for example, I could literally start to click here or anywhere here and start to build a path around the room. And then what you do with it is you take it and well, I've got it tethered right now because I'm not on a wireless network, but I would use the controller to drive it around the room and slowly start to chart that path. Yep. Okay. I'm just getting the 3 minutes and I'm going. Yeah. Okay, perfect. I got 3 minutes and then I got to go outside. So that the librarians have been just wonderful here. So that's the story on that side of the equation. That's how you train it. And then you get into road following where you can do some interactive tweaking. But once you put it in autonomous mode in road following, which happens all the way down here, the error message, but the car will actually run itself around the track. And there's a lot of subtleties here with how many epochs you're going to train it and blah, blah, blah. But we could talk about that maybe another time if you guys end up coming out for a meetup. Let me go back to my PowerPoint here because I don't want to get the librarians angry at me. Okay, we covered that. We covered this. We covered the code. Oh yeah, just before. So there's a bunch of different options out there. JetRacer is one of them. Duckytown is very interesting as well. NVIDIA JetRacer, DIY Robocars, Donkey Car, as Alex mentioned, Amazon Web Racer, Amazon Web Services Racer is another variation, as is f110th.org. Hopefully in this quick thing, we've got a little chance to whet your appetite. Love to see you guys build some cars or make some bots that we could raise. We're toying around with putting together a very customized track that enables higher speed as well. We'd love to do some things at Lawrence Tech. We're traditionally out of Washtenaw Community College, but we can go do things in different locations. Would love to branch out. And with that, I am going to start packing my stuff up here and at least move outside. I will keep listening, but let me turn it over to Saheb and we can come back to questions and when I go outside. But for Saheb, was part of, as Alex said, our tomato bot team. We're working on a delivery bot now, and Saheb's going to introduce a little bit of that delivery bot. But you know, motor controllers, knowing where you are, mapping, deciding how you're going to navigate, what kind of sensors you're going to use, whether it's an autonomous race car or a bot doing deliveries or driving around the greenhouse, they're all variations on a theme. So I'm going to pack up. I'm going to shut my cameras down. I will keep listening. Saheb, over to you. Are you good?
Yep.
Oh, I got to stop sharing. I will do that.
Yeah, thank you, David. Yeah, talk to you later soon. Okay, Sohab, please start. Yep.
Right. 1 minute. I'm trying to share the entire screen.
So you'll find,
that's
you
good.
know, green
Yep.
button. Yeah, I see it. Yep.
All right. So this is actually, if you can see my camera as well as my screen. So my screen is actually showing the delivery bot is actually the same robot as the farm bot. In fact, you can put any module on it. So right now the module on it is a thermal camera and a Raspberry Pi camera. And yeah, you can just drive it with either ROS. So right now, we aren't using ROS right now. It is just using controllers because the ROS implementation, the one we have, does not work with controllers. And there you go. And with the thermal camera, what we can do is we can detect people. We can point the camera at plants and get IR data if you need to. So right now there's a tomato plant that you, I'm not sure if there's enough light to see the tomato plant. Sorry, potato plant, not tomato. Tomato is what we originally trained on, but yeah, you should be able to see plant over here and the thermals for the plant and the human thermals. And in terms of components, yeah, these are actually, this thing is not using any ESC or anything.
Saheb?
This is just using the Raspberry Pi 3.
Saheb,
And
Yeah, maybe you can stand in front of the camera so I can kind of try to make out your image, the thermal image for a sec.
Yep, sure. Can you
Yeah.
see me?
Yeah, there you go. Even if just hold it there for a second. So yeah, you get a heat map basically. And so in COVID times, it's really useful for taking temperature and stuff like that.
Yep. And you can easily hook up any components on it. Other components, if you don't want thermal camera, you can just replace that part of it, put any other component. And yeah, this is exactly the same bot as the FarmMate bot. Right, and I think that's about it.
Oh, CJ, as I'm walking out, if you wanted to show that video before we get into questions and answers, that's how everything fits together.
Okay, yeah, I'll share the video. Just a minute.
And the video is kind of rough. That's in my garage, but you know, it just shows you how these things all do come together. We wanted to do some high-speed runs at Lawrence Tech, but that'll have to be a future thing. But hopefully you'll get a sense of how it works in the short video.
Yeah, so now first, thank you. I'd like to thank SoHype. Thank you so much for your demonstration. I'll share one video. Okay. Okay, I'm sharing.
Maybe while the video is playing, Dave, can you touch maybe a little bit on the, like, did you put those boxes there with the blue and yellow tape on purpose so that the car would have more clear points of references?
More referenceability, the better, beyond just a track. So I put them there to mix it up, but also as the training was progressing for crashes. Unfortunately, in that particular car, the tech is very exposed. So here you see me using the controller. I flip it over into autonomous mode, set the controller down, and the car has learned through the neural network to drive around this track. You'll see it's not simply line following or staying in the middle. I trained it to start to try and approximate a race line. So that's why it's cutting some corners and trying to go a little bit quicker. We're kind of experimenting with how fast these things could actually go. So, but yeah, the more in the pure visual system, actually in any system, if you're using LiDAR or just a cam, the more features you have in LiDAR or with a camera, the better.
Mm-hmm.
Okay, so David, I think it's time for question and answers. Do you have some other slides to show? Oh, okay, you can't show the slide. Yeah. Okay, I think time for questions then.
I think we're right on time too, right?
Yeah, right. So yeah, please, ask some questions. Yeah, we have one chat. Okay,
So I
so
think there was a question about the calibration of the thermal camera with respect to the temperature. It's a good question, and it's a relative value, but I think I'll let Saheb handle that one.
Yep. So the temperature calibration depends on the minimum and maximum values you want to detect. So by default, it is, I think, between 10 and 25. But this particular camera that we are using, this is a very low cost camera and a very, very low resolution camera.
Low cost means like we got a thermal camera for $40 from Adafruit, I believe.
Yep. So this one doesn't have that much range. At a higher cost, you can have a much more granular control of the camera.
The range is roughly 6 meters.
Yep.
Max.
okay, thank you for the question. Any other questions?
David, I have a question for David. It seems to me that major stumbling block is a lack of perception and understanding of the environment, and that's an AI problem. When do you anticipate that there might be a solution? In other words, an AI that understands its environment and has a coherent model, can develop a model from vision, sort of like based on the human model, where we look around the room or look around in the natural environment and immediately recognize the objects and their properties and their relative distances and spaces. When do you think that'll happen for the autonomous vehicles?
Well, so, if we think of it in the context of for the vehicle about, there's navigational focus, and then there's, if you will, contextual focus, understanding even more about these objects. In other words, at a basic level, the car can detect, let's say, that there's a human, or the car or the bot for that matter can detect that there's a human or an object, at the intersection at a very basic level. The camera can detect it too. It can decide if it's a human, or it can just say there's something I see there. Now, when you go further and say, is that thing likely to step in front of me or not, and start talking about, what kind of behavior you can predict or what kind of attributes you can assign to that object, that's, there's tons of stuff left to be done on that front, and it's just getting into deep simulations and deep sort of algorithms and predicting and statistics, and is it even right at the end of the day? And if it's 99% right, is that good enough to go live with? So on the one hand, again, you're kind of almost getting towards AGI, or average general intelligence even, but from a simplistic perspective, and for trying to find things that one can monetize around, just to keep it more tangible and more executable, I tend to, preach the focus is more one of, okay, you're going from point A to B without hitting anything. That's the fundamental goal. You don't have to know whether that's a seal or a dog on the right. As long as it's not in your way, you're fine. If it gets in your way, stop. So at a kind of very, very low level, which it's just about recognizing, impediments in your way and moving from space A to point B. And I think where we're going to see a huge, and that's not that big a challenge at all, if you leave all the context out of it. In fact, an autonomous drone, you can have that right out of the box, as I mentioned in chat, simply by using waypoints, because you're not going to run into anything in the air, most likely. So, navigating a drone autonomously is an out of the box feature with open source software in the form of Q ground control or otherwise. But in the car and in the ground, again, it's really, you have to look at the specifics of the use case and what's called the ODD, or the operational domain definition. So if you're just running stuff, say around a college campus or around a warehouse going from A to B, that's not that horrific a challenge to go do without bumping into things, which is where 90% of the activity and revenue from robots is going to be. Cars, represent 8% of the US economy. Ag represents a lot more. So, working around, say, an agricultural situation, you don't have the same hassles that you do riding in open public and in the wild. An autonomous vehicle at level 5 to go in any kind of rain from Detroit to Los Angeles, if you just, any kind of road, any kind of weather, you just plug it in, that's a very, very long way off. But it's also, to me, a use case of who cares? I don't drive to Los Angeles very often, so the short runs, knowing the route, and more, bots that do a service for you is what I just find a little bit more interesting. And more practical. I think people shouldn't measure the autonomous space on, cars that go across the country or all sorts of different weather conditions. If your camera's blind and your LiDAR is blind, you're blind, period. So, and that happens. So, focus on the more tangible use cases first, where there's much more low-hanging fruit, like picking fruit, for example. If that answers your question at all.
Well, I carry on with your thought there, because I think the picking fruit problem is still not solved even after 20 years of research. What's the holdup?
Oh, I would come right back at you and say there's
That's
tomato
a good
pickers
question.
out there.
Good
There's
question.
apple
We tried
pickers
to
out
solve
there.
that.
you know, they're out there. Google them. You'll see them. And there's starting to see more commercial ones available too. There isn't a bot for every fruit, and the bot that picks the tomatoes, and you can Google them. They're out there. The bot that picks the tomatoes can't pick apples, you know, but there's the bots are going to start coming out of the woodwork. And that's now the other question, of course, is how far do they have to run? Again, comes back to the use case scenario. If you have a half acre, you know, full of tomato plants and you need to get those picked, there's many a solution you could choose from to get that done right now. If you have 52 acres and you've got pumpkins, it's a little different story. But so you'll see right now, if you look at bots to do weeding, bots to do, you know, to zap weeds with laser or pick weeds, we're kind of like, it's coming out of the boxes now, and nobody really owns the territory yet. So you should be, and you see the bot to cut your lawn, you see the Roomba to vacuum. You know, one of our groups is also working on a wheelbarrow that just follows you around. You can find examples of those out there, but they're not, you know, well advertised, they're not commercialized, so you can still get in there even with the DIY space. But again, it comes back to the use case. How much weight is it going to carry? How far does it have to go? Is it going to be on streets? Is it going to be on mud? You know, what kind, that all dictates what kind of wheels and drivetrain you use and what kind of sensors and motors, the whole thing. So I think I would expect to see more and more utility bots out there.
Okay, thank you, David. Any other questions? Actually, I have a question for David. So you showed a demo of your racer car. How many minutes did it take to train that track?
So for the track that I had there, and it depends also on which kind of technology you're using, whether you're using Donkey Car or let's say JetRacer. In that particular case, so collecting the photographs, and you can get away with less in the JetRacer context because you don't have throttle for every single image. But I probably took 100, ultimately 150 in the first batch, and then another 50 of the car facing different directions. And that took, you know, 25, 35 minutes. Putting that then into the network, I think I trained it for 10 epochs, and that probably took, I did not have, so you can train in the Google Cloud if you want. I did not. I trained right on the little Jetson Nano. And I think to go with, you know, around 100, 150 images, 10 epochs took maybe close to an hour. And then to tune this, so yeah, about an hour just working all by itself, crunching on the Nano to build that network. And then it was probably, I don't think I had to do much more to it after that. For that small little track there, it was fairly quick. So certainly everything from step one, which is just to go to, you know, Balena and etch an SD card with the image, the NVIDIA JetRacer image, well, it's Jet card, but you'll see it from the code. So from when I started Balena up and made the SD card all the way through doing the first runs, in that case, because it's a small track in the garage there, soup to nuts within 4 hours.
Okay, thank you. Yeah. So I stop recording.